do it.
Welcome to our final presentation for the semester of Signals and Systems. I'm Sophia.
I'm Shane.
And this is our synth audio manipulation extended presentation. So as we've already talked about these things in class. So actually we have more for you now. We have MATLAB demos and additional content. But in addition to that, we will quickly run over intro to envelopes, R waves, attack, decay, sustain, and release, breakdown, how envelopes change waveforms, and real-world examples. Do you want to do this?
Sure. What is an envelope? A way to describe how sound changes over time. It controls the loudness of a shape or note and makes simple waveforms like the ones we're using, which is like the sine, square, sawtooth, and triangle, sound like real instruments through different types of modulation. Why envelopes matter? Without envelopes, every sound would start and stop instantly. Envelopes add expression, character, and natural feel. It's essential in synthesizers, recording, and sound design.
I got it? Okay. So initially, we started with these 4 waves, and as you'll see in our examples, I personally will use the sine wave and the sawtooth wave, but all these waves can be used to generate sound. So the sine wave is often used in musical instruments and like string instruments, and it has a smooth, pure tone and contains only the fundamental frequency. Which is not the case in instruments, as you'll see in the future. They're actually layered. However, you can have sine waves at different frequencies that can be combined. Additionally, there's the square wave, which, as we all know, alternates between high and low, and you can control the duty cycle to have different effects. And then the sawtooth wave, which is very relevant in string instruments because you kind of bite, like the bow will bite a little bit and then like cool off, and so that helps mimic some natural sounding waves. And then the triangle wave, I personally don't use, but it has more of a quieter, smooth sound because the harmonics drop off at 1/n squared. And some different ways to manipulate the waves, which we went over in class, but briefly, you can change the frequency to a higher or lower pitch, you can change the amplitude, add envelopes. The square, like I said, you can change the duty cycle or add envelopes or filter it. The sawtooth you could filter with a low-pass filter to have classic warm synth sounds, or use detuning to have super saw sounds, and then apply envelopes. And then the triangle, again, you can create bell tones with slow decay or change the frequency.
So for our demo, we had 4 different waves. So this is just the unmodulated, which is sine, the square wave, sawtooth wave, and the triangle wave, all at 440 hertz. So for the ADS breakdown, as we've already said, it stands for attack, decay, sustain, and release. So if you look on this left figure, the attack is the buildup towards the peak of the sound. So it's similar if you would press a piano key, it's that buildup for when it like hits its highest, hits loudest note, and then the decay part is when it goes from that peak sound to when it slowly dies off and then into the sustaining region, which is when you hold down the note, and then when you let go, it will go into the release, and that time is the amount of time it takes to go from sustain to 0. And this is just more elaboration for it.
So some real-world examples, which I will get into later. There's the piano, which has a fast attack, so it sounds like a hammer hitting the string or piano key instantly, and then the sound quickly settles, and it doesn't sustain unless it's held, and it has a short release when the key lifts, whether it's held or quickly tapped. And then violin, or what I'm going to do is the cello, it can either have a slow or fast attack depending on how you want to make the sound, and then you control the sustain with the bow, and it has a smooth, it can also, again, because you have more control, you can have a smooth release or a quick release with the string. And then drums have instant attack, kind of what you would think when you think of a drum sound. It's burst, and then it has a very short decay. And then synth pads you can change all of these things, all of these parameters much easier because you're actually like programming them in. And then these are some examples for the OP1 synthesizer, which I also mentioned in class. there's different types of synth pads and notes and sounds you can make, but some of the types that you can have are cluster, for example, adds grouped oscillators, so it has like a thick harmonic spread. It's not just within like n integers of the natural frequency. You could have like digital, so kind of adjacent to like a square wave, but slightly different. You can add more aliasing and like harmonics onto like a square wave to get more digital-like sounds. And then the FM synth can be fast or medium attack, and then the release can be long, producing smooth tails, which are some things that you wouldn't necessarily be able to control in the traditional instrument.
So this is the example of how envelopes change each waveform. Specifically, for this example, we have the sine wave and the square wave. And so this is the raw wave, which is totally unedited. And then this down here is our ADSR envelope. And so you can see that as this oscillator signal goes into this envelope, you can see how it changes. And so right at the first part, you can see how the attack builds up, the decay goes down, and then this is the long sustain, and then the release. And then you can continue to edit it to build different shapes. But if, for example, we're doing like a pluck of a guitar string, it would just be a fast attack and a fast release. And that'd be it. No sustain and no decay. It would just be like that, basically.
And if you zoom in really close to here, you would see the square wave versus the triangle wave. So this isn't actually all one block. This has the square and the triangle wave within it.
If we zoomed in, exactly. So one of the other things we tried out for testing this is the low frequency oscillator. It operates at very low frequencies below the audible range that we can hear, and it's used to modulate parameters like filter cutoff, amplitude, and the pitch. It adds movement and expressiveness to a sound so it doesn't feel static. And so first we have our time domain plots, and so once again we have a raw oscillator sound, which is for this example is the sawtooth, and then we have the ADSR filter, and then we have the low frequency oscillator, which we can see as this red line right here, and then this is just the amplitude ADSR. And so you can see that this filter, the output of here is no longer perfectly straight because of how the oscillator changed the envelope in the wave itself. And there's more explanation on that on this slide. And now we talked about the Fourier transform before and after. So for the sawtooth wave, once again, it has the harmonics at every iteration. So we can see at each harmonic that it's there. And then we can see that after the Fourier transform, that the low-pass filter reduced the higher frequency harmonics, and the lower frequencies remained dormant, creating a warmer sound. And the harmonic spacing stays the same, but the amplitudes themselves are reshaped, which we can see that as an example, specifically how these are more built up like mountain shapes instead of a straight line, how it was before. And lastly, we did a spectrogram of this, and specifically for the visualization of the harmonics. So once again, we are using the sawtooth as a demonstration, and so you can see that there's high energy at every harmonic present in the sawtooth. But if we were to use other periodic waves, like this sine wave that has like 0 harmonics, right?
Not necessarily. It depends on the instrument.
It does depend on the instrument.
But often there are harmonics which create the like more whole sound that you hear. It's not like whenever you hear a sound in nature, it's never usually just like one sine wave. It's usually like a series of harmonics at that same frequency, at least for like instruments with a string.
Yeah, but the conclusion is that you can see the energy at each harmonic, and so depending on which waveform you chose, the spectrogram would look very different.
And then Shane can grab his computer now.
Okay, so for my demo, I had a larger focus on the ADSR idea, so I was able to put together this rudimentary synthesizer demo that just plays from C to B. It's a little loud, but like, and we can switch from this. So what you just heard was the saw wave, but we also have this square wave, which has the more retro 8-bit sound, and we have the triangle, which sounds a lot more peaceful, and then the sine wave as well. And I'll demo with the sine wave. So as I talked about, as we talked about earlier in the slideshow, there's the attack, which is this slider, the decay, sustain, and release. For this code, you can't like max out everything, otherwise it'll give you an error, so you need to split it up a little bit better. But like, you can kind of, so if we put the attack really high and we lower the decay, the sustain, and maybe like a higher release. Wait, there we go. And so we could hear how it took longer to attack. Or if we had a really long attack but really low everything else, we can hear the build up for those notes. But then I also talked about with the Fourier transform of the low frequency oscillator. And so that's what these sliders are. And so right now, this is what it sounds normally. And that's no low frequency oscillator. I'll use the square wave so you can hear it better because it's also louder. So if we turn up the low frequency oscillator, like up to 9, you can hear it oscillating in the sound. And then you can change the frequency cutoff of the oscillator as well, as long as it's rate. So whether it's really like low, like high, like really slow building up tides, or really fast back and forth. But yeah, that's my demo. Thank you.
So moving on to my part, or what I was very curious about, the reverse engineering audio. So I was like curious, if we wanted to make a violin sound, how could we do that, for example? So just to start off, a little bit of background, how do we actually perceive sound? So a speaker is essentially just a motor with a small range. So it has a single moving coil that is permanently but flexibly wired to the voltage source. And then that coil moves in a field, when there's a voltage applied. And so that allows the magnet to produce force on the coil. And that allows for this part right here to actually push the cone up and down based on the amount of current that's flowing through this loop bouncing off the magnet. So that's how a speaker kind of works. And then essentially what sound is it's just a pulse of air, energy that then creates a vibration in the air around us, and then that vibration makes it all the way to your eardrums, and then that is what actually produces, or how we interpret sound. So one interesting thing that I learned is that this thing called the overtone series is kind of the bread and butter of how sound works with different instruments. So like Shane showed in the spectrogram, there's actually frequency components at n integer multiples of the fundamental frequency. So but the difference is that for every instrument or every sound, the ratio at these different integers, at these different harmonics is different. So as you can see here, the cello has a higher spike there, as opposed to the piano has higher spikes initially and then they kind of fade off, whereas the trumpet has a varying amount of frequency at these different stages. So just in words, and so you can see it, the first frequency is the fundamental frequency, and that's the root pitch that defines the note you hear. And then there's the second octave, which is doubling the frequency, but the same note, but an octave higher. And then the third through perfect fifth, that's when you triple the frequency. And then the fourth, fifth, and sixth add just more complexity to the sound. And so why instrument sounds differ is because every instrument plays the same fundamental frequency for a given note, but the relative strength, like I was saying on the previous slide, differs for each harmonic, which creates its unique timbre. And the simple math, like we said earlier, is the fundamental frequency times some integer number, and then these where the harmonics end up. So this was an interesting video I watched from the University of Madison, Wisconsin, where they played different sounds, and you could kind of see the oscilloscope and then the frequency plot. So this was a guy playing the A note on a cello, just like open A, and then this was what the plot looked like. And so I was curious because Shane had generated these like sine waves and triangle waves and applied filters to them, but they still didn't sound like instruments to me. So I wanted to see like how do we actually construct the wave that an instrument would have, and what does that wave actually look like. So here you can see that this is what the cello wave looks like on an oscilloscope that you would perceive with your ear at the A frequency, and you can kind of see on here it does have those like n integer multiples of the fundamental frequency, which is what, I don't know off the top of my head, but whatever the fundamental frequency for A is. And so yeah, some more theory about this. So the oscilloscope, this was like referencing also this. So that top graph you saw was the oscilloscope, and it has the complex jagged waveform is the sound pressure over time. And one really cool thing, which we'll get to in a couple slides, is that these waves like interpose on each other literally like on the string, on the physical string itself. So like you can have these like half waves and like janky looking waves on the like physical string, and that janky looking wave is actually what goes to your ear. It's not just like some like theoretical thing, it's like rooted in a physical property, which is kind of cool. And then the bottom is the frequency domain, and each spike represents the harmonics. So when you bow a cello string, you're not actually creating a clean clean vibration at a certain frequency. It is the like multitude effect of all of these different harmonics, literally physically at once. And so you can actually simulate this on MATLAB. So that's what this plot is, because I thought this was like a little hard to read. So this is a MATLAB simulated plot, and you can see here the fundamental frequency is 217 hertz. And then you can see kind of the additions of like 2 times that, 3 times that, 4 times that, and then 5 times that. And it's pretty consistent. And so I'll demo what that actually sounds like in a little bit. So yeah, so some more theory continued. This is what I was alluding to earlier. These are like the fundamental frequency, and then it's literally these half waves, which we learned, at least I learned about in modern physics a little bit. So like, yeah, this is just like the waveform. And so like one question I had is, how can you hear them all at the same time if they're all, you know, like if you just have the third harmonic? Well, actually, the cool thing, which I said earlier, is that they're all interposed. So your string isn't going to look nicely like this. It's going to be some combination of all of these different frequencies. And it's because when you pluck a bow or string, you're not creating independent vibrations. You're creating the literal physical system that's constrained at the nut and the bridge. And the string can only vibrate at frequencies where a whole number or half wavelengths fit between those 2 points. So then you do end up with the same harmonics, it's just literally physically on the bridge of the cello. And so yeah, I did some simulation based on this YouTube video that I saw earlier. I wanted to kind of like simulate these myself. So we have the cello in MATLAB, and just adding, like you can add harmonics, and then you can add like different like filters, I guess, to represent what the cello would actually look like. And I'll play these for you later so you can see the differences. And then I did the same thing with the piano. Just started with like perfect integer harmonics, and then stretched the harmonics, and the upper partials go sharp. And then for like the third stage, 3D tuned strings and hammer position modeling. So like when you press the piano key, you want it to like have that hammer effect. And then it has a 2 decay envelope, which simulates reality more. And then again, I did this with the trumpet because I wanted to see if you could simulate the trumpet. So initially just the simple harmonic series, and then add like a couple peaks at these different times to simulate how the trumpet actually sounds. And then there's a brassy attack, delayed vibrato, added like a breath and noise layer, and then have some formal resonances too. And so you can kind of see, like, although all of these are playing in theory like the same note, their frequency spectrums look very different. So that's like the main difference between instruments, is that although they're playing the same note and they could be at the same harmonic spacing, like we saw earlier, the frequency graphs look very different. And these are just kind of like some of the differences written out. So yeah, Shane can demo his MATLAB code first, and then I'll demo mine, and then we'll call it a wrap. And so yeah, these are our sources. So for my demo, we're gonna start off with the cello, and it just has the sawtooth-like decay. We have the cello tone synthesized, but then we also add the envelope for the attack and the sustain, like we talked about. And so that's just the first sound. That's just a plain cello with these harmonics and some attack and sustain. And then next, the cello is better demonstrated using a sawtooth wave because of the bowing. So if we start with just the sawtooth, and then we add the harmonics, and then we add the filtering, it sounds closer to an actual cello. And then the next one that I simulated was the piano. So this is just the basic. And then when you stretch the harmonics, and then this actually sounds like a piano key. And then again with the trumpet, we start with just the basic trumpet, and then we add the different harmonics, and then this is the full model, which actually sounds like a trumpet. And that is my MATLAB demo.